Hi everyone. This is a lesson on the theories of continental drift and plate tectonics. So we would start this activity by I give out a whole series of um, cutouts of the continents, and on each one of the continents there are pictures of either rocks or fossils. And what you would do is you would try and sort out the continents to see if there's some sort of pattern when it comes to the geology of the continents and the fossils. And what you would find is that, for instance, Africa, in the northwest corner where the Atlas Mountains are, the rocks there match up with the rocks that are found on the east coast of the United States and um, extending all the way up along the coastline of into Canada. And then those rocks also match up with the rocks that you would find in Norway and Scotland, suggesting that perhaps those places used to be connected when those mountain ranges were being created. But unfortunately, if you're at home today, you're going to miss out on that activity. So instead, we'll just take a look at a quick little animation here. And oops. Uh, what we've noticed is that, why doesn't this animation work? Well, I guess I'll have to skip over it for now. So, first thing we need to realize is that what you and I call a theory is completely different from what scientists call a theory. For instance, um, somebody has eaten the last cookie in the cookie jar in your house, and you have a theory that it's your sibling because you didn't eat the last cookie, and you're figuring that more than likely the other culprit would be your sibling. Now, that's just an educated guess. You don't have any evidence, but that's your working theory that you have. Scientists, on the other hand, don't use the term theory. That would be a hypothesis. A hypothesis is an educated guess. Then you go out and collect a whole bunch of data, and either that hypothesis is fulfilled or not. And um, when lots and lots of research have been done on a particular topic and everything keeps on pointing in the same direction, and what you can do is start being able to predict based on those patterns, you start having the building of a scientific theory. So, for instance, the theory of flight, you know, the Wright brothers had a hypothesis that if they had enough lift to their machine, that it would be able to stay in flight for a certain length of time. And they put that to practice, and of course, more and more aircraft are being developed, better understanding of the concept of aer- aerodynamic design, and now we have lots of theories that revolve around flight. So when it comes to continental drift and plate tectonics, there is literally a mountain of evidence that supports these theories. But what we're going to do today is take a look at the evolution of continental drift and see how it can be a challenging process to go from a hypothesis to a theory. So there's this guy, Alfred Wagner, and he's a German scientist, not a geologist though. Um, but he noticed that when you take a look at the continents, they seem to fit together in many cases if you look at the ancient coastlines. And he also knew a lot about fossils. And he was finding some peculiar fossils, patterns of fossils that suggested that perhaps the continents were joined when these particular species were alive. And so his working hypothesis is all the continents were joined together during the Paleozoic period in a supercontinent called Pangaea. And this massive continent would allow any species to travel from any continent to another continent. Uh, might be a bit of a challenge to walk that far, but nevertheless, um, that's what was possible at that time. Eventually, the northern continents all split off. So Laurasia is made up of Asia, North America, and Europe. And Gondwanaland was this big supercontinent that broke off to the south. It included Africa, Oceania, South America, Antarctica, and believe it or not, India used to be its own continent. It's a bit of an oddball because it actually goes from the southern hemisphere to the northern hemisphere. So, here we go. This is the animation I was looking for. So, this is taking a look at, now they're calling it plate tectonics because that's the modern theory, but the original concept was called continental drift. So, if you go through this video, you can see um, we've got Laurasia on the top here. We've got North America, Europe, and Asia in the northern hemisphere. We have this thing called the Tethys Sea, which separates the southern continents of Gondwanaland from it. And slowly but surely over time, you're going to see the movement of these continents. And I'll let you watch that on your own time. So, what evidence did he have? Well, if you take a look at the coastlines of certain continents, they seem to fit together like a jigsaw puzzle. So, this is, the first and most obvious piece of evidence. If you take a look at this edge of Africa, you'll notice it fits nicely into the states of the Carolinas and Georgia, and the Atlas Mountains that are found here match up uh, quite nicely with the Appalachian Mountains of those states. If we take a look at the fossil record, we've got something. I'm not saying that T Rex was the example he was using, but if you look at Tyrannosaurus Rex, you got a gigantic monster of a species with these tiny little arms. There's no way that thing can swim, and it certainly can't swim across an ocean. And what we're finding is that you would find fossils of something like a T Rex in North America, Europe, and Asia. Now that it sounds sort of plausible. Maybe there was a land bridge between Asia and North America, and therefore they could have crossed there. But when you have something like Brontosaurus that's found in South America, Africa, Oceania, and Antarctica, it's like, well, how did it travel around all of those continents, but didn't make it up to North America or to Asia? Because if you take a look now, Africa is connected to Asia. So um, whenever these animals existed, those continents must have been connected if they were land animals, and you could find them on each one of these continents that are now separated by oceans. Now, of course, it wouldn't matter if it was some sort of swimming thing like fish, and it certainly wouldn't matter if it was a bird. So it's got to be a land animal that we're using as our evidence for the fossil record. So here we have a couple of different species. So whatever this thing is here is found in both South America and Africa in this range. And we've got this species here found in Antarctica, India, and Africa. So how is it that, we got this strange looking beast that obviously can't swim far, is found on three continents that are separated by huge sections of ocean now? And here we've got a plant, possibly the pollen blew across the ocean, but that's not very likely because if that's the case, why wouldn't it have blown up into North America, Asia, and Europe? So it's a pretty convincing argument that this fossil record supports that the continents must have been joined at one time in a different pattern than they are today. And then the last one is if you take a look at the rock record, you'll see along the coastlines of many places. For instance, here we have Norway matching up with the mountain range in Greenland. We've got the mountain range here, the Atlas Mountains and the Appalachians matching up, and so on. So, once again, it would be quite odd that we would have this pattern just form naturally. Whereas if they were joined at one time when those mountains were being created, that would make a lot more sense to explaining this pattern. So Wagner goes to the powers that be, and he presents his evidence, and they laugh him out of the room, and rightfully so. Fine, you've got all these great patterns, but how do you move a continent? He didn't have any way to explain the process, and so he went off to Greenland to go find more evidence, and he ended up dying on the glacier there, and that was the end of continental drift. It wasn't until after World War II where we had developed sonar and started studying the bottom of the oceans, that we started to realize that, wow, the ocean isn't just this big flat area. There's huge mountain ranges in the bottom of the oceans. And we also started to understand a lot more about earthquakes and the fact that our planet is made up of three sort of mega layers. We've got the core, which is really hot, it heats up the mantle, and the mantle we know is somewhat liquid. I liken it to heating up a pen with a what call it, a lighter. The pen can become soft enough that you can move it around, but it's not really liquid, right? So anyway, we got this mantle, and it's heating up and moving around, and so the plates, which are what we're standing on, um, move along with those currents, and as a result, the surface of the planet is broken up into these big, gigantic plates. Sometimes those plates are colliding with each other, and sometimes they're separating away from each other. So when they're colliding, in this case, we've got a really dense ocean plate colliding with a continental plate. The ocean plate goes underneath, or as we call it in scientific terms, it subducts underneath. And as it does, it goes down, it gets heated up in the mantle and melts, and then it sometimes bubbles up to the surface and creates a volcano. So a lot of BC is full of ancient volcanic um, mountains. But also, when you have these two plates colliding, it's folding up and bending this continental plate and making mountains also. Sometimes we'll have two continental plates colliding. So, in the case of India, colliding with Asia, as it continues to push into Asia, it's bending the land and folding it into the massive Himalayan mountains and the Hindu Kush mountains, and so you get a pattern that looks more like this. This is a collision zone. And then finally, at the bottom of the Atlantic Ocean, we've got two plates pulling apart because we've got this hot spot coming up in the middle, and it's causing separation. Lava comes out, especially if you look at Iceland. There are huge rift areas where you'll have 20, 100-kilometer long crack in the surface. Suddenly, all this volcanic fountain comes out and produces new material. So the bottom of the Atlantic Ocean has this massive mountain range, and some of the times that mountain range reaches to the surface, like in Iceland. And this pushing apart, of course, is going to eventually cause the plate on the other side to collide with some plate on the other side of the planet. So those are the three main ways plates are moving around. And this is a great documentary explaining, so please watch it. Good old story of Alfred. Oh, and that's the end of the slideshow. So I hope you enjoyed.